Chapter 15: Building Streaming Services. An order validation ecosystem. Having developed a basic understanding of Kafka Streams, now let's look at the techniques needed to build a small streaming services application. We will base this chapter around a simple order processing workflow that validates and processes orders in response to HTTP requests, mapping the synchronous world of a standard REST interface to the asynchronous world of events, and back again. Download the code for this example from GitHub. Starting from the left-hand side of the figure 15.1, the REST interface provides methods to post and get orders. Posting an order creates an order-created event in Kafka. 3 validation engines: fraud, inventory, order details, subscribe to these events and execute in parallel, emitting a pass or fail based on whether each validation succeeds. The result of these validations is pushed through a separate topic, order validations, so that we retain the single writer relationship between the orders service and the orders topic. When the results of the various validation checks are aggregated back in the orders service, which then moves the order to a validated or failed state, based on the combined result. Validated orders accumulate in the orders view, where they can be queried historically. This is an implementation of the CQRS design pattern, C command, query responsibility segregation on page 61 in chapter 7. The email service sends confirmation emails. The inventory service both validates orders and reserves inventory for the pure chase, an interesting problem, as it involves tying reads and writes together atomically. We look at this in detail later in this chapter. Join filter process. Most streaming systems implement the same broad pattern where a set of streams is prepared, and then work is performed one event at a time. This involves 3 steps. 1. Join. The DSL is used to join a set of streams and tables emitted by other services. 2. Filter. Anything that isn't required is filtered. Aggregations are often used here too. 3. Process. The join result is passed to a function where business logic executes. The output of this business logic is pushed into another stream. This pattern is seen in most services but is probably best demonstrated by the email service, which joins orders, payments, and customers, forwarding the result to a function that sends an email. The pattern can be implemented in either Kafka Streams or KSQL equivalently. Event-sourced views in Kafka Streams to allow users to perform a HTTP GET, and potentially retrieve historical orders. The orders service creates a queryable event-sourced view. See the event-sourced view on page 71 in chapter 7. This works by pushing orders into a set of state stores partitioned over the 3 instances of the orders view, allowing load and storage to be spread between them. Because data is partitioned, it can be scaled out horizontally. Kafka Streams supports dynamic load rebalancing, but it also means GET requests must be routed to the right node, the one that has the partition for the key being requested. This is handled automatically via the interactive queries functionality in Kafka Streams. 2. There are actually 2 parts to this. The first is the query, which defines what data goes into the view. In this case, we are grouping orders by their key, so new orders override old orders, with the result written to a state store where it can be queried. We might implement this with the Kafka Streams DSL like so. The second part is to expose the state stores over an HTTP endpoint, which is simple enough, but when running with multiple instances, requests must be routed to the correct partition and instance for a certain key. Kafka Streams includes a metadata service that does this for you. Collapsing CQRS with a blocking read. The orders service implements a blocking HTTP GET so that clients can read their own writes. This technique is used to collapse the asynchronous nature of the CQRS pattern. So, for example, if a client wants to perform a write operation, immediately followed by a read, the event might not have propagated to the view, meaning they would either get an error or an incorrect value. One solution is to block the GET operation until the event arrives, or a configured timeout passes, collapsing the asynchronicity of the CQRS pattern so that it appears synchronous to the client. This technique is essentially long polling. The orders service, in the example code, implements this technique using non-blocking I/O. Scaling concurrent operations in streaming systems. The inventory service is interesting because it needs to implement several specialist techniques to ensure it works accurately and consistently. The service performs a simple operation. When a user purchases an iPad, it makes sure there are enough iPads available for the order to be fulfilled, then physically reserves a number of them so no other process can take them. Figure 15.3. This is a little trickier than it may seem initially, as the operation involves managing atomic state across topics. Specifically, 1. Validate whether there are enough iPads in stock, inventory in warehouse minus items reserved. 2. Update the table of reserved items to reserve the iPad so no one else can take it. 3. Send out a message that validates the order. This will work reliably only if we enable Kafka's transactions feature. Ensure that data is partitioned by product_id before this operation is performed. The first point should be pretty obvious. If we fail and we're not wrapped in a transaction, we have no idea what state the system will be in. But the second point should be a little less clear, because for it to make sense we need to think about this particular operation being scaled out linearly over several different threads or machines. Stateful stream processing systems like Kafka Streams have a novel and high-performance mechanism for managing stateful problems like these concurrently. We have a single critical section. 1. Read the number of unreserved iPads currently in stock. 2. Reserve the iPads requested on the order. Let's first consider how a traditional, i.e., not stateful, streaming system might work. Figure 15.4. If we scale the operation to run over two parallel processes, we would run the critical section inside a transaction in a shared database. So both instances would bottleneck on the same database instance. Stateful stream processing systems like Kafka Streams avoid remote transactions or cross-process coordination. They do this by partitioning the problem over a set of threads or processes using a chosen business key. Partitions and partitioning was discussed in Chapter 4. This provides the key, no pun intended, to scaling these systems horizontally. Partitioning in Kafka Streams works by rerouting messages so that all the state required for one particular computation is sent to a single thread, where the computation can be performed. 3. The approach is inherently parallel, which is how streaming systems achieve such high message at a time processing rates, for example, in the use case discussed in Chapter 2. But the approach works only if there's a logical key that cleanly segregates all operations, both state that they need, and state they operate on. So splitting, i.e., partitioning, the problem by product_id ensures that all operations for one product_id will be sequentially executed on the same thread. That means all iPads will be processed on one thread, all iWatches will be processed on one, potentially different, thread, and the two will require no coordination between each other to perform the critical section. Figure 15.5. The resulting operation is atomic, thanks to Kafka's transactions, can be scaled out horizontally, and requires no expensive cross-network coordination. This is similar to the map phase and map reduce systems. The inventory service must rearrange orders so they are processed by product_id. This is done with an operation called a re-key, which pushes orders into a new intermediary topic in Kafka, this time keyed by product_id, and then back out to the inventory service. The code is very simple: orders.select key_id, order, greater than order.get product, / re-key by product_id. Part 2 of the critical section is a state mutation: inventory must be reserved. The inventory service does this with a Kafka Stream state store, a local, disk-resident hash table, backed by a Kafka topic. So each thread executing will have a state store for reserved stock for some subset of the products. You can program with these state stores much like you would program with a hash map or key/value store, but with the benefit that all the data is persisted to Kafka and restored if the process restarts. A state store can be created in a single line of code, then we make use of it, much like a regular hash table. Writing to the store also partakes in Kafka's transactions, discussed in Chapter 12. Re-key to join. We can apply exactly the same technique used in the previous section, for partitioning writes, to partitioning reads, for example, to do a join. Say we want to join a stream of orders, keyed by order_id, to a table of warehouse inventory, keyed by product_id, as we do in Figure 15.3. The join will have to use the product_id. From warehouse inventory.product_id. This is what would be termed a foreign key relationship in relational parlance, mapping its primary key onto order.product_id, which isn't its primary key. To do this, we need to shuffle orders across the different nodes so that the orders end up being processed in the same thread that has the corresponding warehouse inventory assigned. As mentioned earlier, this data redistribution step is called a re-key, and data arranged in this way is termed co-partitioned. Once re-keyed, the join condition can be performed without any additional network access required. For example, in Figure 15.6, inventory with product_id equals 5 is collocated with orders for product_id equals 5. Re-partitioning and staged execution. Real-world systems are often more complex. 1 minute we're performing a join, the next we're aggregating by customer or materializing data in a view, with each operation requiring a different data distribution profile. Different operations like these chain together in a pipeline. The inventory service provides a good example of this. It uses a re-key operation to distribute data by product_id. Once complete, it has to be re-keyed back to order_id so it can be added to the orders view, Figure 15.7. The orders view is destructive, That is, old versions of an order will be replaced by newer ones, so it's important that the stream be keyed by order id so that no data is lost. There are limitations to this approach, though. The keys used to partition the event streams must be invariant if ordering is to be guaranteed. So in this particular case it means the keys, product id and order id, on each order must remain fixed across all messages that relate to that order. Typically, this is a fairly easy thing to manage at a domain level, for example, by enforcing that, should a user want to change the product they are purchasing, a brand new order must be created. Waiting for n events. Another relatively common use case in business systems is to wait for n events to occur. This is trivial if each event is located in a different topic, it's simply a three-way join, but if events arrive on a single topic, it requires a little more thought. The orders service, in the example discussed earlier in this chapter, Figure 15.1, waits for validation results from each of the three validation services, all sent via the same topic. Validation succeeds holistically only if all three return a pass. Assuming you are counting messages with a certain key, the solution takes the form 1. Group by the key. 2. Count occurrences of each key, using an aggregator executed with a window. 3. Filter the output for the required count, reflecting on the design. Any distributed system comes with a baseline cost. This should go without saying. The solution described here provides good scalability and resiliency properties, but will always be more complex to implement and run than a simple, single-process application designed to perform the same logic. You should always carefully weigh the trade-off between better non-functional properties and simplicity when designing a system. Having said that, a real system will inevitably be more complex, with more moving parts, so the pluggability and extensibility of this style of system can provide a worthy return against the initial upfront cost. A more holistic streaming ecosystem. In this final section we take a brief look at a larger ecosystem, Figure 15.8, that pulls together some of the main elements discussed in this book thus far, outlining how each service contributes, and the implementation patterns each might use. Basket writer/view. These represent an implementation of CQRS, as discussed in command query responsibility segregation on page 61 in chapter 7. The basket writer proxies HTTP requests, forwarding them to the basket topic in Kafka when a user adds a new item. The Confluent REST proxy, which ships with the Confluent distribution of Kafka, is used for this. The basket view is an event-sourced view, implemented in Kafka Streams, with the contents of its state stores exposed over a REST interface in a manner similar to the orders service in the example discussed earlier in this chapter. Kafka Connect and a database could be substituted also. The view represents a join between user and basket topics, but much of the information is thrown away, retaining only the bare minimum, user id list product. This minimizes the view's footprint. The catalog filter view. This is another event-sourced view but requires richer support for Pagina tie-in, so the implementation uses Kafka Connect and Cassandra. Catalog search. A third event-sourced view. This one uses Solr for its full-text search capabilities. Orders service. Orders are validated and saved to Kafka. This could be implemented either as a single service or a small ecosystem like the one detailed earlier in this chapter. Catalog service. A legacy codebase that manages changes made to the product catalog, initiated from an internal UI. This has comparatively fewer users, and an existing codebase. Events are picked up from the legacy Postgres database using a CDC connector to push them into Kafka. The single message transforms feature reformats the messages before they are made public. Images are saved to a distributed file system for access by the web tier. Shipping service. A streaming service leveraging the Kafka Streams API. This service reacts to orders as they are created, updating the shipping topic as notifications are received from the delivery company. Inventory service. Another streaming service leveraging the Kafka Streams API. This service updates inventory levels as products enter and leave the warehouse. Archive. All events are archived to HDFS, including fixed T1 and T10 point-in-time snapshots for recovery purposes. This uses Kafka Connect and its HDFS connector. Streams management. A set of stream processors manages creating latest/version topics where relevant. See the latest version pattern in long-term data storage on page 25 in chapter 3. This layer also manages the swing topics used when non-backward compatible schema changes need to be rolled out. CHAN. Dealing schema change and breaking backward compatibility on page 124 in chapter 13. Schema Registry. The Confluent Schema Registry provides runtime validation of schemas and their compatibility. Summary. When we build services using a streaming platform, some will be stateless, simple functions that take an input, perform a business operation, and produce an output. Some will be stateful, but read-only, as in event-sourced views. Others will need to both read and write state, either entirely inside the Kafka ecosystem, and hence wrapped in Kafka's transactional guarantees, or by calling out to other services or databases. One of the most attractive properties of a stateful stream processing API is that all of these options are available, allowing us to trade the operational ease of stateless approaches for the data processing capabilities of stateful ones. But there are of course drawbacks to this approach. While standby replicas, checkpoints, and compacted topics all mitigate the risks of pushing data to code, there is always a worst-case scenario where service-resident datasets must be rebuilt, and this should be considered as part of any system design. There is also a mindset shift that comes with the streaming model, one that is inherently more asynchronous and adopts a more functional and data-centric style, when compared to the more procedural nature of traditional service interfaces. But this is, in the opinion of this author, an investment worth making. In this chapter we looked at a very simple system that processes orders. We did this with a set of small streaming microservices that implement the event collaboration pattern we discussed in Chapter 5. Finally, we looked at how we can create a larger architecture using the broader range of patterns discussed in this book. About the author. Ben Stopford is a technologist working in the office of the CTO at Confluent Incorporated, the company behind Apache Kafka, where he has worked on a wide range of projects, from implementing the latest version of Kafka's replication protocol through to developing strategies for streaming applications. Before Confluent, Ben led the design and build of a company-wide data platform for a large financial institution, as well as working on a number of early service-oriented systems, both in finance and at ThoughtWorks. Ben is a regular conference speaker, blogger, and keen observer of the data technology space. He believes that we are entering an interesting and formative period where data engineering, software engineering, and the life cycle of organizations become ever more closely intertwined.